All right, so we're gonna have a review today on chapter 6 for exam 4. And I can't dilly-dally. That doesn't mean you can't ask questions. Right, if you have questions, definitely we're gonna cover them. By the way, anybody have any problems from the review document or any other problems that we need to deal with first?
I think I was struggling with number 14.
Amber?
Yes.
Okay, 14. Okay. That's on my list. We will get to that one. Anybody else? Okay. I've got just about an hour to cover this many, and that gives me average of 2 minutes per. So I can't digress any. Let's scoot it over here. There we go. Number, see if I can get 2 and 3 on there together. All right, number 2. What's the kinetic energy of 1.56 kilogram object moving at 94 kilometers per hour? Okay, so the mass of the object is 1.56 kilograms. And it's moving at 94 kilometers per hour. So velocity is 94.0 kilometers per hour. All right, so how are we going to solve this problem? We know how to calculate kinetic energy, don't we? Okay. Kinetic energy equals 1/2 m mass times velocity squared. The trick to this problem is to be sure your units are right, because energy is supposed to come out in units of joules. So that means that mass and velocity both have to be SI standard measurements. Right? Mass has to be kilograms, and this would be a derived unit. Velocity, meters is the standard length, and seconds is the standard time. So it'd be meters per second for velocity. All right, we're okay here. Right, that's good. This one has to be converted to meters per second. All right, so we do a little dimensional analysis here. I'm going to start working on the time sign first. So we need to get rid of hours. Oops, where's my eraser? You do that one again. Hours. We need to get rid of hours. This is in the denominator, numerator, and leave us with seconds. Right? Do we know how many seconds are in an hour? Or do we need to chain conversion? We know how many seconds are in a minute, how many minutes are in an hour. Right? So we can do that. We know this one, 60 minutes in an hour. That gets rid of hours, but now we're stuck with minutes, so we've got to get rid of minutes and seconds. So 60 seconds in a minute. Okay, now we're good for seconds. That is not going to last either. All right, now we need to do kilometers. We need to fix kilometers, make it into meters. All right, kilometers is in the numerator there, it has to be in the denominator here. So the relationship is how many meters are in a kilometer. Right, what does kilo mean? 1,000. So they have to be 1,000 meters in a kilometer. And that gets rid of kilometers. Hours are gone, minutes gone, left us with seconds and meters. So that was the thinking part. The rest of this part is number crunching. So we'll just say 94 divided by 60, divided by 60 again, and times 1,000. And that's, let's see, I'm going to keep a bunch of decimals around it later.
I can't hear you for some reason.
I'm sorry? You can't hear me? Obviously. Okay, let me see what's going on here. stop the share so I can access this part of it. Let me test my. That works. Testing. Okay.
I couldn't hear him at first either, but if you're on your phone at the top, there's a little, it looks like a volume thing, and mine was turned off. If you just click that, it'll, like you can hear him again. At least that's what worked for me.
Oh, on your end.
Yes, on my end.
Okay. Okay, let me reshare. Should be right where we left it. Yep. Okay. So now, let's see, I ended up with 26.11 meters per second. Okay, now that we have the standard units of measure correct, we can put them into the formula. 1.56 kilograms and meters per second is 26.11 squared. Okay, I've already got this one in my calculator, so I'm just going to square it. And then times 1.56 and then divided by 2. And I get 5.3. Now I'm gonna obey the rules. 3 significant figures times 10 squared joules, but it's in kilojoules. Okay, so you can either use dimensional analysis and fix this to make it kilojoules, right? Or you can expand it into a standard notation, which would be what? 2 here, 2 there, 532. Actually, I think it would be better to use dimensional analysis. We want kilojoules. So there are 1,000 joules in a kilojoule, right? So when you bring this one from the denominator to the numerator, what happens to the sign? It goes negative, right? That becomes a negative 10 to the minus 3. Once we bring it up here, so 10 to the second and 10 to the minus 3 is what? Right? When you multiply bases by powers, the same base by different powers, you just add the powers. So 2 and a minus 3 is a minus 1. So that would be 5.32 times 10 to the minus 1 kilojoules. All right, and there it is, A. Okay, did I lose anybody on this? Are you trying to scratch your head and remember algebra class or math class? All right, that's 2. And that ate up more time than I expected. Let's do 3. All right, which of the following statements correctly describes the signs of Q and W for the following exothermic process? At pressure equals 1 atmosphere, temperature equals 370 K. All right, so the process they're talking about is a phase change where water vapor is converted to water liquid. Okay, so this is remember what that's called. Remember when we did the triangle earlier in the semester? This is called condensation. It goes from a gas to a liquid. And it's an exothermic process. Does that make sense? Right? You're going from a gas with high energy molecules to a liquid with lower energy molecules. Right? So it is an exothermic process. Does it give a value? No, it just says exothermic. So the delta H is negative. Okay, that's what we know so far. Let's see what else. Pressure equals 1 atmosphere. This may be necessary and it may not be. And temperature is 370 K. All right. What do we know? Which of the following statements correctly describes the signs of Q and W? we want to know something about Q, the heat that's released, and the W, any work that's being done. So it helps to draw a picture, I think. If we have this gas confined with one atmosphere, if we have the water vapor in here, and the water vapor is going to water liquid, right? So it's going to form a liquid on the bottom. Then what's happening? If this pressure is constant, what's going to happen to that piston? It's going to drop, isn't it? Right? So if this is our system and these are surroundings, then as this piston drops, let's look at work first. What work is being done? Right? Is there work being done on the system, or is the system doing work on its surroundings? When a gas contracts like this, the work is being done on the system. So if work is being done on the system, that means this is positive. Right? Everything is relative to the system. So if work is being done on the system, it's positive value. How about Q? Well, we know what Q is, right? It's negative. As long as the pressure is constant, Q is equal to delta H. So this is negative and that's positive. So which one would that be? C. Q is negative, W is positive. Okay? All right, let's scroll to the next one or two. 7. Okay. 1 mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters against a constant external pressure. So we're going with our piston again under a constant external pressure of 1 atmosphere. So that's equal to P. And the gas is expanding from 1 liter. And so maybe it started down here. This was 1 liter. And now the total volume is 8.93 liters. Okay. So based on what we just talked about, as this gas expands, it's doing work on the surroundings. Right? So W is negative. It may not ask us that, but I thought I'd just stick that up there to keep things in perspective. How much work in joules is performed on the surroundings? Okay. What's our formula for work? Equals negative pressure times change in volume. Remember? Okay. So what's the change in volume? It's going from 1 to 8.93. Remember, it's final minus initial. 8.93 minus 1 is the change in volume. How about pressure? Well, pressure is 1 atmosphere. Okay, that's a negative. All right, so we have what, 7.93? W equals 7.93 liter atmospheres. Now, everything you do to the units has to the number has to be done to the units. So we have liters here times atmospheres, liter atmospheres. Those are the wrong units, right? We want it in joules. So now we have to use a conversion factor, which they give us there. 1 liter atmosphere is 101.3 joules. So a liter atmosphere is 101.3 joules. So now all we have to do is multiply those two together. 7.93, 101.3 times. Let's see. It's in joules. All right. So I get, let's see, 3 significant figures. 8.03 times 10 squared Well, they've got it in standard notation, correct? And this is negative. Nobody caught me. Equals negative 803 joules, right? So that should be B. Okay. That formula should be in useful information. You may want to check, see, be sure. All right, 7 and 12. Calculate the work associated with the compression of gas from 121 liters to 80 liters. So it's going from here, 121.0 liters, down to 80 liters. Okay. And under constant pressure of 13.1 atmospheres. All right, this one's easy. Actually, this one's easier than the last one. Right. W equals negative P delta V, and negative pressure would be 13.1 atmospheres times final minus initial, 80 minus 121.0 liters. For especially for this chapter, that final minus initial is extremely important because the sign that you come up with tells you which ways the heat is moving or which way the work is being done. And when you use that formula where it's 0 equals Q1 plus Q2 plus Q3 and all, the sign makes a huge difference. If you mess the sign up, then you're going to come out with the wrong answer, guaranteed. All right. So we got 80 minus 121. So that's going to be a negative number. Right? Negative 41 times 13.1. Okay. And then a negative times that. So we have a positive, work's being done on the system. That makes sense. It's positive. Let's see, 3 significant figures here. Yep. 5.37 times 10 squared liter atmospheres. Okay. Well, let's see, they've got standard notation. 537 B. And notice one of your choices up there has a negative sign in front of it. So if you mess up the negative, then that's the one you're going to pick. Right, that was 12. We're almost there. I think the next one is the one that let's see. Enter Alexis. At least for the lecture. All right. Here we go. Now 14 through 17. So let's see, what are the conditions for these 4 questions? A gas is in a 1 liter bulb at standard temperature and pressure. So gas is in a 1 liter bulb. That's volume at standard temperature. What's standard temperature for a gas? 0 degrees, 273 K. It's temperature. And pressure. Standard pressure is 1 atmosphere. Okay, those are the beginning conditions. Hooked to another bulb that's evacuated. Okay. All right, so we've got a valve here, and then we've got another bulb. It doesn't say what its volume is. I don't think it's important actually. But this pressure equals 0. All right. When the valve between the two bulbs is open, then come the questions. 14 is what is the true about the value of Q? And we're talking here in terms of, is it zero? Is it greater than zero, less than zero? In other words, is it positive or negative? Or is it just nothing? Okay, that's what this means. So Q, let's look at the rest of them while we're at it and get them all up there. 15 is W. 16 is internal energy. And 17 is enthalpy. Okay. Remember one thing. It may not be pivotal to explaining what's going on here, but one thing is these two are state functions. These two are path functions. Okay. So this only matters what happens at either end. Doesn't matter what happens in between. And these depend on what path does it take. All right. So let's look at what's internal energy? Internal energy is Q plus W. Enthalpy is internal energy plus P delta V. Work is work and Q is Q. All right. So notice one thing that's happening here. The pressure is going to change because this is at 1 atmosphere and that's at 0. We know when we open the valve, it's going to go that way until it equalizes. We don't know what it's going to be at the end because we don't know the volume here, so we can't use Boyle's law. But it also says that the temperature does not change. Temperature is standard temperature and it stays that way. Whatever has to happen, it stays that way. So if this is the system, then if the temperature doesn't change, then Q has to be 0. There's no heat transfer at all if the temperature is constant, right? Because heat is calculated based on the movement, based on difference in temperature. If the temperature is constant, Q has to be 0. Okay. Now, inside this bulb, the movement of that gas from this bulb to that bulb and to equalize, is it working against an external pressure? Well, the internal pressure, of course, is 1 atmosphere, but the pressure on the outside is not affecting what's on the inside. So there's no work being done either, right? The gas is just moving. It's not doing any work at all. It's not working against a constant pressure, moving a piston. It's not a bulb that expands and contracts. These are solid bulbs and they stay that way. So there's no work being done either. Okay. So that makes this one easy, right? 0 plus 0 is 0. How about an enthalpy, right? Well, if this one is 0, what about this one? Pressure times volume. Well, the pressure times volume over here is 1. What is it when we get finished? Well, as we know that according to Boyle's law, if pressure goes up, volume goes down, right? They're directly proportional. So this is unchanging. Whatever happens here is unchanging. So we could say something about delta H, but I'm pretty sure that delta H is 0 also. Moving on. By the way, what's the driving force behind that gas moving? What's making it move? We can't blame it on heat, right? A reaction or phase change or anything like that. right? Why is it moving over there? We know it's going to. I mean, that's intuition. Gas will expand into a vacuum, but we can't say why yet. That comes in second semester. We talk about a little tidbit called entropy. So hold your breath, we'll get there. How about 18? I think 18 stands alone. Of energy, work, enthalpy, and heat, how many are state functions? Right, I just told you that one. Two of them are state functions, aren't they? Enthalpy and energy. Those are both state functions. All right. 19. Oh, I needed to ask, was it Amber? I mean, did that clear anything up for you, Amber? I guess not. Which of the following properties are intensive properties? Okay, so we've got 5 of them. The bottom one is energy. This one is concentration, volume, temperature, and mass. What does it have to be an intensive property? The amount doesn't matter. The property is constant with a changing amount of whatever. So, how about mass? That changes with amount. The more you have, the more mass you have, right? So that's not intensive. How about temperature? You can have something this size or this size, and if they're at the same temperature, right? Who cares how big it is? So that's one. Temperature. Volume. The more stuff you have, the more volume you get, right? So that's not it. Concentration. Yeah. Concentration, right? Molarity. When you have a certain amount of something per unit volume, then you have a concentration, and it doesn't matter how much you have. Concentration is the same. And energy. Total energy. That's an extensive property. This is extensive, intensive. Oh, so that would be 2 and 3, 2 and 4, excuse me, 2 and 4, C. Okay. Did I mess up?
No.
You lost the concept of intensive versus extensive? Okay. Extensive, just ask yourself, does the value assigned to that property, does it change with the amount of stuff? So if you got more stuff, mass changes. If you got more stuff, volume changes. If you got more stuff, temperature won't change. And concentration is a ratio. A lot of intensive properties are ratios, something per something else. And that's one clue. If you have that, if you have a ratio of something, then you're talking intensive property. Temperature is a little different because it's just a single value, but it represents the average kinetic energy of the substance. So if you have more substance, the average kinetic, it doesn't matter. More substance at the same temperature. All right. 19. Who's next? 23. No, can't get 24 on there. 23. Consider the reaction. What's C2H5OH? I recognize that. Ethanol. The drinking kind. We're going to burn it and get carbon dioxide and water. Now, the authors of this question were kind enough to balance the equation for us and give us the delta H. Right? Consider the following propositions. The reaction is, rather than write it up here, that would take too much time. what can we tell about this equation? Right here. We can tell that it's exothermic. If delta H is negative, the process is exothermic. In other words, the system is giving up heat to its surroundings. So in an alcohol burner, underneath that big plate, metal pan of food, well, sometimes they use methanol. Sterno, right? Sterno heaters, right? It's giving off that heat. And that's what keeps food warm. Well, it used to be. Now I think they probably use heat lamps or resistive heaters under. That's safer than an open flame. Consider the following propositions. The reaction is endothermic? No. The reaction is exothermic. Roman numeral 2. The enthalpy term would be different if the water formed was gaseous. Okay, think about that for a second. It would be, right? Why would it be? If the water term were gaseous, then you're eliminating that phase change from gas to liquid out of the calculation, right? So you've got the chemical change that's based upon those liquid, gas, gas, liquid. Now, if you make it liquid, gas, 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 then you don't have the water phase change that would be required to estimate the enthalpy. So yes, the enthalpy would be different. So this is one case where the phases of your reactants are extremely important for determining the enthalpy of a reaction. Those phases are essential. 2 and 3, which of the propositions is true? 2 and 3, E. Okay. All right. 24. How much heat is required to raise the temperature of 5.75 gram sample of iron with that specific heat from 25 to 79.8? All right, so we've got 5.75 grams of iron. It's our mass. And temperature change. Right? Initial temperature is what? Raise the temperature from 25 degrees or 0 degrees C to a final temperature of 79.8 C. Okay, and then the other thing, a bit of information they gave us was the specific heat of iron. And let's see, what are the units? 0.450 joules per gram degree. Okay. Now, what formula are we going to use? Remember? Right. Q equals the specific heat times the mass, assuming, and this is in terms of mass, not moles. Right? It could be moles, but in this time it's mass, times the change in temperature. And the question is, how much heat is required? How much heat has to go in here? Is it going to be an endothermic process? Yeah. Right? It's going from this, the system is the iron. We're going from 25 degrees to 79 degrees. We're putting energy into the system, so it's going to be a positive value. Right? So Q equals this one. I'm going to, and I guess I better put the units in. See, and then mass has to be in grams, right? Remember, when you've got an equation with a constant in it, the constant determines the units of measure. It's like PV equals nRT. R is the gas constant, and its units determine the units that have to be for the other variables. In this case, we need grams as a mass, which we happen to have. Right? And check your dimensional analysis here. Grams in the denominator, grams in the numerator, they cancel. Now, final temperature minus initial temperature for delta T. So it's 79.8 minus 25.0 degrees C. And degree C is in the denominator here in the numerator there, so it cancels and leaves us with joules. That's what we want. Joules is our measure of heat. Okay. So now, I'm gonna do this one first. It's inside the parentheses. 79.8 and 25 minus, and this is 54.8 degrees. Yeah. So this together is 54.8 degrees C times 5.75 times 0.450. And this I get, let's see. That's 3, 3, and 3. Well, this is a constant, so it doesn't matter. Just these two matter for significant figures. This is an exact number. All conversion factors are exact numbers. So 142 joules, 142 joules. And that's a positive value, right? This big number minus this little number means this is a positive. Positive, positive. So this is positive. 142 E. Okay. That formula is also in useful information. All right. 26. .5 gram piece of aluminum, which has a molar heat capacity of 24.03 joules per degree C mole, is heated to 82.4 degrees C and dropped into a calorimeter containing water with a specific heat capacity of 4.18. Initially at 22.3. The final temperature of the water is 24.2 degrees. Ignoring significant figures, calculate the mass of the water in the calorimeter. All right. Are we given information for the calorimeter? No. We have to assume the calorimeter has no impact on the transaction. We leave that Q value is gone. It's not used in this one, which we know is not real, but for our purposes. So I think it's important to organize your thoughts. Right. First of all, we're going to know that in this calorimeter, everything that happens in there is equal to 0. So we're going to have the Q for the aluminum and the Q for the water. Okay, we know that. Now let's organize our thoughts here. Q for aluminum is going to be S times moles. Notice the Q for aluminum is in terms of moles. So this is going to be moles, not mass of aluminum, times its delta T. But the Q for water is going to be S times mass delta T. Okay? That's the first place that could trip you up, is recognizing that difference. Okay, if we're going to have moles here, then we got to find out how many moles is 32.5 grams. If the mass is 32.5 grams of aluminum, we need to convert that to moles. Right? Everybody remembers how to do that. Somebody else dinging? The only one I'm missing is Kathy. Somebody must have dropped out and come back. Okay, aluminum is 2698 grams per mole. Okay. So let's get that one done. 32.5 should be greater than 1, shouldn't it? 26.98 divided into it. 1.205 moles. We're told to ignore significant figures. Okay. in case you're wondering. Okay, so if we set this up, we need, let's expand it. S for aluminum is given as 24.03. 24.03 joules per mole degree C. The number of moles is 1.205 moles of aluminum. Delta T, what's the final temperature for the final temperature of the water is 24.2. You drop hot metal into it, and eventually it's going to come to an equilibrium temperature where both the metal and the water are the same temperature. That is 24.2. So 24.2 degrees minus what's its initial temperature? 82.4. Right. So that's going to come out with a negative number, right? This one's bigger than that one. How about the water? Well, we know that the water is 4.18. They're only using 3 significant figures. Joules per gram degree C. And then the mass of the water is the question. What is the mass of the water? How about change in temperature? Got the same final temperature as the metal, right? Because they came to equilibrium at 24.2 degrees minus its initial temperature, 22.3 degrees. 24.2, 22.3 degrees C. There we go. Now we got it all set up. We just have to solve for this unknown right here. All right. So we can do this one in one calculation, right? There's no unknowns in here. So what's this difference? 24.2 and then 82.4 subtracted. This is a negative 58.36 times 1.205 times 24.03. So that's equal to a negative. I'm going to write this in standard notation. 1685 joules. Then over here, we have, let's see what this value is right here. Can we do that in our head? 1.9 degrees C, is that right? Let me see, let me add it together. Trying to be 2, here's 1, 3, 4. Yeah, that's right. 1.9 degrees Celsius. Okay. Times 4.18. So these two together are 7.942 times the mass of the water. Okay. Let's do this one times that difference, and that's a positive value. And so it's still positive here. This one's negative. 7.942 times the mass of the water. So now we need to solve for the mass of the water. Well, if we move this one on this side, then we have 1685 joules equals 7.942 times the mass of the water. And the mass of the water then would be, I'll just write the whole thing out so nobody will get lost. 85 divided by 7.942. What happened to the negative? Then we have a negative in there. We lost it when we crossed the equal sign. Just checking. Okay, so 1685, 7.9. I already got it in my calculator, so I'm just going to hit the divide button. Okay, 212 grams. 212 grams of water is how much was in that calorimeter. What this problem illustrates is setting up one of these problems, calorimeter problems. You can have any one of these variables can be unknown. And you can solve for it as long as there's only one of them, right? You could solve for initial temperature. You could solve for final temperature. You could solve for what's the S of aluminum if you have everything else. So it's just an algebra problem after you've plugged everything in and you got one unknown. From there, I mean, it's just math. All right. Let's see. Where it keeps, oh, Kathy's there. All right. Any questions? Calorimeter problems are the kind of problem where you need to stay extremely organized. Right? You can't do this stuff in your head. You got to write it down on paper, write it on the board, get all your factors identified, and then put them in the right place, and then go to work on the solution. If you try to do it, if you try to take shortcuts, then 9 times out of 10, you're going to lose. All right. Let's see. Let's take them in order. I was about to say if I run out of time, when I run out of time. And the other folks show up, then we'll go in the lab, and if I have to, I'll come back and finish it. Okay, 27. A 45.9 gram sample of metal is heated to 95.2 degrees and placed in a calorimeter containing 100 grams of water at 21.6 degrees. The final temperature of the water is 24.5 degrees. Which metal was used? So we're going to use the specific heat as determined by our equation to identify which metal it is. And here again, I noticed that they left the calorimeter out of the calculation. I guess just to simplify it. So we still have that equation. Here equals the Q of the metal plus the Q of the water is our equation. Well, let's see. If we expand that again, like we did before, then we have, this is our unknown, Q of the metal. I'll just put an M there. And the mass of the metal, and the change in temperature of the metal, plus the Q of the water, I mean the S of the water, we know that. We know the mass of the water, and we know its temperature change. So we know everything here, and we know everything here except for that value. So we can solve for that one and find and propose which metal it is. All right, so this is going to be our unknown. What's its mass? 45.9 grams. Okay, that's the right unit of measure because this is going to be in, we look at all the specific heats, they're all in joules per gram degree. So this grams, okay, grams, and delta T, right? What was the final temperature of the metal? It's the same as the final temperature of the water, 24.5 degrees. Right? Minus its initial temperature, which was 95.2 degrees. Okay. So we got that part. Now the next part is water, 4.18. Are they still using just 4.18? Yeah. Joules per gram degree C. And the mass of the water is 120 grams. Right. And the change in temperature, final temperature of water is the same as the final temperature of the metal, 24.2, because they're in the calorimeter together when they reach equilibrium. But the water starts out at 21.6. There we go. Yeah, we've got no unknowns here, so we can do this whole calculation. And that'll come up with one value, 24.2 and 21.6.
24.5.
Excuse me.
24.5.
Thank you. Thank you. That's saving me some trouble at the end. There we go. Let's try that again. 24.5 and 21.6 minus, so I get 2.9 degrees times 120 grams times 4.18 is our specific heat for water. So for this part of it, I get 1,455 joules. Okay. Grams cancel, degrees cancel, that's just with joules. On this side, we've got this value here, 24.5 minus 95.2. Did I get that one right? Yeah. So that's a negative 70.7 times 45.9, which is a negative 3,245. Okay. So this value plus this value equals 0. All right. So if we put this one on that side, then it becomes a positive. All right. 3245 S for the metal equals 1455 joules. And then SM, the specific heat for the metal, is 1455 divided by 3245. And I come up with, let's see, 0.448 joules per degree C grade. Looks like the closest one is iron, doesn't it? We rounded it off to 2, it would be exactly. Did I lose anybody? Okay. Hearing no objections. The more of these you work, the easier it gets, actually. Which is true for a lot of things in chemistry. Did I skip 28? I did. Thank you. You take 295 grams of a solid at 30 degrees and let it melt in 425 grams of water. The water temperature decreases from 85 to 30. Calculate the heat of fusion of this solid. Okay, this is going to be one of our, let's see the part 2 or part 3 today, where we dissolve a solid in water and measure the temperature change. In this case, it gets colder. So that's an endothermic process. Okay. But the setup is very similar. Right? In the calorimeter, you have several things going on, and they're ignoring the calorimeter again. So what happens? Well, the heat of fusion is one factor. The heat of solution. I don't know why they say heat of fusion. Oh, it melts. Okay. So this is not actually going into solution. We put it in water and it melts. So it's not going to be absorbed by the water. It's not going to go into solution. Something like, I don't know, a polyolefin, fat or wax or something, sometimes be a good example. In the hot water, it would melt. And then we have the other factors are speaking to what happens to the water. So our unknown here is that entire factor right there. What's the heat of fusion? Well, actually, that's not the final answer. That's the total heat that's been absorbed by the material to make it melt. But heat of fusion is an intensive property. It's ratioed to the mass or the moles of the substance. We've got 295 grams. And we look at our answers, joules per gram. All right. So in the end, we're going to have to take this value and divide it by 295.5 grams. Because we need heat per grams. But we got to get this one done first. So 0 equals Q fusion plus the Q of the water, which is same as always. Okay. All right, so Q of the water is again 0.4, excuse me, 4.18. 4.18 joules per gram degree C. The mass of the water, 425 grams. And the change in temperature for the water, what's the final temperature? 30 degrees. Minus the initial temperature, 85.1 degrees C. All right. So we have 0 equals Q fusion plus whatever that comes out to be. So it's going to be a negative number, 30, enter, and 85.1. Did I get that one right? You give me second guessing myself now. This is minus 55.1. Right there. Times 425 times 4.18. And this value is now a negative. Let's see, do I want to do this? 97885. 1, 2, 3, 4. Yeah, joules. Okay, so the Q of fusion, I just bring that to the other side and then we swap them, is 97885 joules. That's for that mass, that total mass of the solid. But the heat of fusion is ratioed to the mass. So the heat of fusion, let's see, delta H fusion, the enthalpy of fusion is 97885 joules per 295.5 grams. And I get 331 joules per gram. C. Okay. We will have to do this step right here. It's not exactly the same, it's similar to it. Because when you get the final value of Q for your experiment, either any one of the 3 experiments, it has to be ratioed to something. Right? The first one is an acid-base reaction. So it'll be ratioed to the number of moles of water produced. So you get a Q, then you divide it by the number of moles of water. And the second and third ones, they're probably ratioed to moles also. So you have a certain mass of sodium carbonate dissolved in water, a certain mass of sodium bicarbonate dissolved in water. You got to convert it to moles and divide it into the Q that you get from your experiment. And then compare it to that chart at the end of the procedure. See how close you are. Okay, 28. And got 8 minutes to go unless we're waiting on somebody, and I'll just keep talking until they all get here. We haven't even used Hess's law yet. All right, 32. In the lab, you mix 2 solutions, each originally at the same temperature. The temperature of the resulting solution decreases. Which of the following is true? So, final temperature is less than initial temperature. That's what they're saying. They started off at the same initial temperature. Well, they ended up at the same final temperature, but the temperature decreased. Final temperature is less than the initial. So that process is endothermic, right? We can say that. It's endothermic. Okay, the chemical reaction does not release energy. That would be exothermic. Right, so it's not A. The energy released is equal to Sm delta T. Well, we don't have any information for that. We mixed two solutions, right? All we have is maybe change in temperature. The energy released is not equal to Sm delta T because that's incomplete. It's equal to the change in temperature of one, the change in heat transfer to the change in heat transfer. The total has to equal 0, right? So that's an incomplete statement. It could be part of the answer, but it's not the right answer. B is an incomplete statement. The chemical reaction is absorbing energy. Well, that's true. It's endothermic. And D is the same way as saying A, which is wrong. So more than one, no, it's just that one, just C. C is the only one out of that bunch that makes sense. Right. 36. Exactly 123.7 joules will raise the temperature of 10 grams of metal from 25 to 60. What's the specific heat capacity of the metal? All right, this is really simple. Do I need to do this? I guess so. If we say Q equals Sm delta T, then we can solve for S. Right, equals Q over M delta T. Now, what's the heat? 123.7 joules. Right. What's the mass? 10 grams. Notice we're building up our S, joules per gram degree C. So the final temperature is 60, and the initial is 25. So all we have to do is run the numbers. The key to this one is solving the equation for the unknown that you want, using the data that you have. 123.7 divided by 10, and then divided by 60 minus 25, which is 35 degrees. Divide that. Okay, so this value is 0.353 joules per gram degree C. B. Right? I should move these around and put the easy ones in the front. Kind of build. All right, 38. On a cold winter day, a steel metal fence post feels colder than a wooden fence post of identical size because we've got a steel post that is made of iron and carbon. That's our steel post. And then we've got a wooden post here. And they're at the same temperature. Right. Initial temperature is exactly the same because they're in the same weather. Okay. All right. When we touch this one, it feels colder than that one. So what does that mean? What does that mean to our senses? Does that mean the temperature of a surface of our skin is decreasing, is further decreased here than it is here? Yeah, because we're sensing the cold more with this one than that one. Then you can also stick your tongue to it. Also, you can see what happens. Like Dumb and Dumber. Okay, so what's happening here? Well, if we say the initial temperature is the same, then the change in temperature will be different. The change in temperature here will be greater than the change in temperature here. Wood versus steel. The change in temperature is greater for this one because it transfers, it makes your finger colder. Right? The specific heat capacity, in other words, for this one, for steel, would have to be less than the heat capacity for the wood. I think that's right. Let's see. The specific heat capacity of steel is higher than the specific heat capacity of wood. The specific heat capacity of steel is lower than that for the heat capacity of wood. The heat capacity of steel is less than it is for wood. I don't know if that's a good explanation. We didn't say anything about the mass. The ability to resist the temperature change is carried within the value. If this is greater than that, then it has a greater heat capacity, wood, than iron does. All right. Consider this reaction. That's the same reaction as we saw earlier, where we're burning ethanol. Three. Rather than write that up there, I'm just going to reference it. When a 21.1 gram sample of ethyl alcohol is burned, how much energy is released as heat? I'm going to have to write it up there because this is how we organize stoichiometry around the balanced equation. Excellent. Let's move this over a little bit. I'll have C2H5OH. Liquids plus 3 oxygens. Gas yields 2 carbon dioxide plus, and this water is liquid also. Okay, and the delta H, delta H equals minus 1.37 times 10 to the third kilojoules. It's a pretty energetic reaction. Just as a reminder, when you have a balanced equation, this has only energy units. And this is the amount of energy released when 1 mole of ethanol reacts with 3 moles of oxygen to produce 2 moles of carbon dioxide, 3 moles of water. So you can ratio it depending on which one of these you have, right? It'd be minus 1.37 times 10 to the third kilojoules per 1 mole of ethanol, if you need that as a conversion factor, or per 3 moles of oxygen, or per 3 moles of carbon dioxide and 3 moles of water. That's how that works. In this case, we're working from an amount of this, 21.1 grams. 21.1 grams is burned in, we have to assume excess oxygen. Otherwise, if we have a certain amount here and that runs out, then it won't consume everything. But if we assume that everything is consumed, now we need to do our stoichiometry, right? Since the stoichiometry is based on moles, this must be converted to moles because that value is per mole of ethanol. So that's why we need that molar mass that was given to us in the problem, 46.07. Okay. We can calculate the moles of ethanol that are consumed in this reaction. 07. Okay, I get 0.458 moles. Okay, this is moles of ethanol, and that's my abbreviation for ethanol. Okay, so nobody's confused. Well, if it's this many moles and it's this many kilojoules per mole, right, for 1 mole here. It's minus 1.37 times 10 to the third kilojoules per 1 mole of ethanol. And this part cancels, and all we have to do is multiply those two together. Let's see. 0.37 exponent 3 times. So this is a negative 627 kilojoules. Now, is our answer in kilojoules? Yeah, it's in scientific notation. 6.27 times 10 squared. Now, there's no sign there. Right? We know it's exothermic because of that negative sign. What it's saying is how much energy is released. That word right there means that the sign doesn't matter. Well, the sign does matter, but in the answer, the sign doesn't matter because we're saying how much is released. Okay, that's a technicality. If it asks us how much energy is transferred, that doesn't say into the reaction or out of the reaction. Then you need the sign to tell the difference. But since we say it's released, then that's how much released. I know it's picky, but I just don't want you to get confused with the absence of the negative sign in the answer. Because you might come to me and say, the answer's not there. All right. 45. Okay, I did it again. I tried to finish exam 4, chapter 6 review. And I went through the entire remainder of the chapter review and was not recording. So that's what I'm doing now. I'm going to pick up where we left off. So let me share the document, the review document. Here it is. All right. And let's see if I can boost it a little bit. Is that too much? Yeah, it's too much. Maybe that'll do. All right. So I gotta make some adjustments here. Okay. So this is where we left off when we went to, when we broke and went to the lab and finished our thermochemistry experiment. Now I'm going to pick up with number 45. Okay. The total volume of hydrogen gas needed to fill the Hindenburg was 2.11 times 10 to the 8th liters at 1 atmosphere and 24.7 degrees Celsius. How much energy was evolved when it burned? All right. Everybody's seen pictures of the Hindenburg. The Hindenburg was what's known as a dirigible. In other words, it had a metal framework and its lifting capacity came from bags that were positioned inside that frame. And in this case, they were filled with hydrogen. Well, they were filled with hydrogen because the United States had a lock on the world supply of helium. And the Hindenburg belonged to bad people, the enemy. So they couldn't get hold of helium, so they used hydrogen.
Hydrogen, in fact, has a higher lift capacity than helium, but it's extremely dangerous. And this is what happened. So what we have here is a situation where the hydrogen itself, combined with oxygen in the atmosphere, produced water and a lot of heat. That negative delta H is an exothermic reaction, minus 286 kilojoules for that reaction. So if we have that gas plus this gas, we get, and this is liters, okay? And delta H, actually it should be a 0 up there. Delta H is minus 286 kilojoules. Okay, you notice one thing about this reaction is it's got a fraction, right? When we learned to balance equations, we prefer not to have fractions in there. Well, that's fine, but the amount of heat evolved is based upon this reaction. If we multiply this by a factor to get rid of that fraction, then we have to multiply this by the same factor. So we're just going to leave it alone and work with it the way it is. Another thing about it is, this is an equation for the standard enthalpy of formation for water. This is water at room temperature and 1 atmosphere pressure is a liquid. And that's the way you start it. You put the product over here, 1 mole of it, and then you work backwards. Right? You take each element, which the elements are stable. For hydrogen, it's stable as a gas, and oxygen, it's stable as a gas also, but they're both diatomic. And then you say, how many hydrogens do we need? Well, the diatomic hydrogen supplies exactly what we need. And the oxygen, though, we need half of that. So this is a formation equation, and this is the standard heat of formation for water. Okay, so we're going to use that information plus the other things that they gave us. Right? We know that the volume of hydrogen equals 2.11, yeah, 11 times 10 to the 8th liters. The pressure equals 1 atmosphere. And the temperature equals 24.7 degrees. 24.7 degrees C. All right. What do we need to know in order to calculate the amount of heat evolved? We need to know the number of moles of that gas, because this is based upon that equation, and this is the amount of heat evolved when we have 1 mole of hydrogen. So if we have the number of moles of hydrogen, we can find out how much heat was evolved. How are we going to get moles of hydrogen out of this? Well, when hydrogen is in the bags and it's not exposed to air yet, then it is under 1 atmosphere pressure and is at 24.7 degrees Celsius. And it's that volume. So why don't we use the ideal gas equation? Right? We've got this one, we've got that one, we've got that one, and this is a constant. So if we solve for n, then we have PV over RT. Okay? So the pressure is 1 atmosphere. The volume is 2.11 times 10 to the 8th liters. And these units are correct. Right? Remember, when you have a constant in the equation, the units of the variables must match the constant. Right? And in this case, the constant is the gas, ideal gas constant, 0.8206 liter atmospheres per mole K. So there's atmospheres, there's liters. We're going to get moles and K. So we need this temperature in K. All right, so we need to add 273. And we can go ahead, since there's a fraction here, let's go ahead and put 1.5. You don't have to. It should work out just fine the other way. But I'm going to do it this way. 297.85. Okay. Okay. Now, all we have to do, that's the thinking part. All we have to do now is crunch the numbers. All right. So 1 times 2.11 to the 8th power divided by 0.8206 divided by 297.85. And I get, let's see, 1, 2, 3, 1, 2, 3, 3 significant figures. Should be 8.63 times 10 to the 6th moles of hydrogen gas. Okay. Now we know how many moles of hydrogen gas there are in that bag, or in the, actually there were several bags in the Hindenburg. All right. The only problem with, let's see. There we go. The only problem with doing this video at home is my board's kind of small. So I've got to erase to make room. All right, we've got that value. Now what we need is how many kilojoules does that many moles represent? Right. So we can take, this is minus 286 kilojoules per mole of hydrogen for that reaction. Right. So it's minus 286 kilojoules per mole of hydrogen. Okay. And now we've got 8.63 times 10 to the 6th moles of hydrogen. So these two cancel, numerator, denominator, and we'll multiply those values together. Let's see, 286 times. So I get, I'll write it right here, minus 2.47 times 10 to the 9th kilojoules. That is a lot of energy. And the answer is D. Now, I put the sign here because that tells me it's an exothermic reaction. But the question says how much energy was evolved. That basically tells you that the reaction is exothermic, that it only wants to know the number. How much energy is evolved? Right? So that's why the answer is 2.47 times 10 to the 9th kilojoules. And that's perfectly all right under the circumstances, the way the question is worded. All right, that was 45. Moving on. Okay, let's scroll to the next one, 46. Okay. This one should be a little easier, it looks like. 46. So we have this equation. We have methane plus chlorine yields carbon tetrachloride plus hydrogen chloride gas with a delta H of minus 434 kilojoules. So based on that reaction, what energy changes occur when 1.2 moles of methane reacts? Right, and then the answers, you'll notice that some of them say released and some of them say absorbed. So instead of putting the plus or the minus sign, we say released for exothermic and absorbed for endothermic. All right, so I'm not going to write the equation up there. What we need to know is the delta H for this reaction is minus 434 kilojoules. And this is per, notice that it's 1.2 moles of methane that we're interested in. And methane is 1 mole in that equation. So this is that many kilojoules per 1 mole of methane. Okay? So all we need to do is take the number of moles of methane and multiply it by this factor, because that cancels and leaves us with the energy. Now this is negative, right? That's not negative. So we know the outcome is going to be negative. Be negative something. Let's see. 434 and 1.2 is negative 5. See how many? Two significant figures right here. So 5.2 times 10 squared kilojoules. That's a negative. So the energy is being released. It's exothermic. Okay. So 5.2 times 10 to the, oh, excuse me. The answer is in joules. The answer is in joules. That's correct, kilojoules. But this means what? 10 to the third. So 10 to the third times 10 squared. What do we do when the base is raised to different powers? You've got 10 to the squared, 10 to the third. You add the powers. So this would be minus 5.2 times 10 to the fifth joules released. So 5.2 A would be the best answer. All right. Moving along. Yeah, I have to. My whiteboard keeps drifting on me. Who's next? Okay. 51. All right. Consider the following specific heats of these metals. They got zinc, magnesium, iron, silver, lead, those values. And the question is, if the same amount of heat is added to 25 grams of each of the metals, so we got the same mass, the same heat, which are all at the same initial temperature, which metal will have the highest temperature? So what we're saying is, when we add heat to these metals, which one will have the largest delta H? They're starting at the same initial temperature. So the highest temperature minus the initial temperature will give us the largest delta T, excuse me, not delta H, delta T. I think what we should do, well, let's put our information up here. Well, actually, we know that they're all same 25 degrees, 25 grams, and starting at the same temperature and the same heat. So if we use this formula, equals S mass delta T, what are our constants? For each one of these, this one's constant. This one's constant at 25 grams. And the amount of heat is constant. They don't say how much, but these are our two variables. That's a constant. So let's put this over here with this other constant. Q divided by N, right? That is a constant value for our purposes. That means now that S times delta T is equal to a constant. All right. Now, what did we learn with Boyle's law? Remember, pressure times volume equals a constant? When the product of two variables is equal to a constant, then the variables are inversely proportional to one another. As this one goes up, that one has to go down. So as this one goes up, that one goes down. Or as this one goes down, that one goes up. Right? So we're looking for the one that has the largest change in temperature, delta T. So if that's the case, and this is constant, then the largest delta T will be the smallest specific heat. And in that case, the smallest specific heat is lead. That means with the same amount of heat and the same mass, lead's temperature will change the most out of that group. All right, so the answer is E. All right, let's get these ABC. Those things give me the heebie-jeebies. Here we go. Now we've got a Hess's law. All right. I can tell already I'm going to have to do some writing and erasing to get all this up on the board. But let's start with the target equation. We want to know, given the heats of the following reactions, right here, all these reactions, given those values, can we combine them in a certain way so that we can determine the enthalpy of this target reaction? So I always put the target reaction at the top, and that's where I start. So 59. And our target reaction is P4O10. P4O10 solid plus PCl5 gas, 6 PCl5 gas yields 10 Cl3 PO gas. Okay. The way you work a Hess's problem is you look at what your target is. You want this one, and that one in the final equation. So you've got to pick it out of the available equations. If we look at Roman numeral 1, we find it's P4Cl2 and PCl3. That's not there. So we don't start with Roman numeral 1. That would be crazy because we don't know what to do with it. So we go to the next one, right? P4 plus 5O2 yields P4O10. P4O10 is here. All right. So Roman numeral 2 is where we start. But notice P4O10 is on the wrong side of the arrow. It needs to be on the left-hand side. It's the right number of moles, right? 1 mole is what we're looking for, but it's on the wrong side. So we need to flip the equation. And when you reverse the equation, you change the sign on the enthalpy. It's reasonable to expect that because one direction, our enthalpy is negative. It's exothermic. But if you go backwards, instead of releasing heat, it absorbs heat. So we just change the sign. So I'm going to write the flipped equation up here. P4O10, like that. And that is equal to, or yields, P4 solid plus oxygen, 5O2. Yes. Now I'm going to have to squeeze the values in here. Now the delta H is going to be plus 1225.6. kilojoules. Okay, that's number 1. I put an asterisk by the ones I'm going to use so I can tell them apart from any of the others that were manipulated in the process. I don't want to get them all confused. So we're going to use this one. That takes care of that side. Now, how about PCl5 or Cl3PO? Well, let's see. Number 3 has PCl5 in it, but it's on the wrong side. And there's not enough of it. We need 6 PCl5. We got to flip the equation, change the sign on the delta H, and multiply the delta H by 6. Right? Because the delta H as written is based upon 1 mole of PCl5, but we need 6 of them. So we have to multiply the delta H times 6 and change the sign because we're flipping the equation. So I'm going to do both of those steps at once. This is 3 modified. All right, we have 6 PCl5 gas. And let's see, I'm going to put a box around this so we don't lose it. And 6 times the other ones. 6 times PCl3 and Cl2. Gas and gas. Okay. Now we've flipped it. We got to change the sign on minus 84.2. Okay. So 84.2, we change the sign in my head. And then times 6. So I get 505.2 plus 505.2 kilojoules. All right. Now, that takes care of this one. How about Cl3PO? Well, it looks like number 4. We'll get that one. It needs to be on the right-hand side. And let's see, it is on the right-hand side, but there's not enough of it. We need to multiply it by 10. That means delta H is multiplied by 10, but we don't change the sign because we're using it in the same direction as it's written. So PCl3, 10 times PCl3, and that's a gas. 10 times 1/2 oxygen is 5 O2s. And then we have 10 Cl3PO. 10 Cl3PO. Right. And we also have the delta H is 10 times that, minus 2857. Kilojoules. Okay. Now, we've taken care of all these, but we've introduced, let's see, we've got that one is kosher, that one's kosher, and this one's kosher. But we've got all these other terms in here that we have to get rid of. Let's see how many we can eliminate. If it's on the right-hand side and the left-hand side by the same mole coefficient, then they cancel. So 1P4. Nope, not there. 502. 502. Right side, left side. 6PCl5. No. 6PCl3. Okay. What I'm seeing is these are not going to cancel correctly. And we have this chlorine in here. And we have that phosphorus in there. So let's go back to Roman numeral 1 and see if it can fix the problem. Roman numeral 1 has P4 plus 6Cl2 plus 4PCl3. If we write it down as it is there in Roman numeral 1, then it will cancel P4. So let's look at it that way. We have Roman numeral 1. Now we have P4 solid plus 6Cl2, 6Cl2 gas yields what? 4 PCl3. 4 PCl3. And we didn't do anything to the equation. So we keep the delta H the way it's written. Minus 1225.6 kilojoules. Now let's see if this equation will help us cancel out the terms that we don't need. All right, so we need that one. We don't need this one. And there it is right there. 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 Okay. This one's good. How about this one? We need this one, but we don't need that one. PCl3. Well, we got a 6 PCl3 and a 4 PCl3, which is 10. And we got a 10 here. So these two on the right-hand side cancel this one on the left-hand side. How about chlorine? Right, there's 6 of those, 6 of those. There, right there. So these are all gone. These are gone. We keep that one. Those are gone. We keep that one. Keep that one. Those are gone. So we cancel all the terms that we don't need in the target equation. And now what we have to do is add up the delta H's. Add up the enthalpies. That will tell us the enthalpy of this equation. So I got, let's see, 2967.3, and then 505.2 added, and then 2857 minus, and 1225.6 minus. Okay, so it's minus let's see. 1, 2. How many? I get 4 significant figures. Yeah, because when you add them together, this one limits them. So I can do now minus 610.1. Does it say we could ignore? No, it didn't say we could ignore. But the closest one to the value we want is B. See how easy it is to make a mistake. Especially when I'm trying to squeeze everything into a small space. All right. That was 59. Next one. Let's see. Here we go. All right. That. There. Center my board again. There we go. Okay. 68. This one goes back to what I was talking about, the standard enthalpy of formation for a compound. In this case, we need to write the correct formula for the standard enthalpy of formation for carbon monoxide and include the enthalpy, standard enthalpy for that. Remember, you start with the product. There you go. Start with the gas. Then you work your way backwards. We need carbon and we need oxygen. Most stable forms. Oxygen's easy. It's a gas under standard conditions. Carbon, though, needs to be graphite. That's the most stable form of carbon under standard conditions. All right, there we go. So we need 1 carbon. We got 1 carbon. We need 1 oxygen. That means we need a half. Okay. And the enthalpy, delta H, F, standard enthalpy is minus 110.5 kilojoules. Now, since we have 1 mole of here and here, that value is per mole of that, or per half mole of oxygen. Either way, we don't have to write the mole. Okay, so the best one here is C. Right, carbon graphite, half oxygen, CO gas. And delta H is minus 110.5. That was fairly easy, I would say. Let's see. 78. One of the main advantages of hydrogen as a fuel. Hydrogen as a fuel. Yes. So if hydrogen is going to be a fuel, what's it going to react with? It has to react with water. Oxygen plus oxygen. And it yields water. Right? So if we write it the way we did before, like this, that would be legal. All right. What the main advantage of hydrogen as a fuel? A is a good choice. The only product of hydrogen combustion is water, right? No carbon. Now, whether or not it produces carbon is immaterial to me personally, but some people place a lot of stock in carbon emissions. Right? I think it's a fool's errand, but that's their choice. Okay, so what about the others? It exists as a free gas. A lot of things exist as a free gas, and they can work as fuels, right? Methane is a free gas. In fact, it's more energy dense than hydrogen is. So B is not a good choice. C, it can be economically supplied by the world's oceans. Well, yeah, right. All you have to do is take water, right, and electricity. Let's see, a DC voltage, and you get hydrogen gas and oxygen gas, right? Let's see. 2, 2, 2. There we go. All right, so you can get all the hydrogen you need from seawater, but that's not its main advantage. Plants can economically produce hydrogen needed. Now, as a matter of fact, it takes a special kind of plant, and it's not what we normally see around us, green plants. Green plants, when they are active, they take carbon dioxide from the air, combine it with water, and make glucose, plus oxygen gas. So oxygen gas for green plants is a waste product. It's not, I mean, it doesn't produce hydrogen anywhere in there. That's why in an earlier lecture, I mentioned the fact that as far as green plants are concerned, carbon dioxide is food. Now, of course, when they do this, they use like H nu. Remember that? H nu is energy, is light energy. Planck's constant times frequency. We did that way back. Or E contains a large amount of energy per unit volume of hydrogen gas. Well, actually, it doesn't. Right? There are plenty of other fuels that pack a lot more energy into a small space. Right? Methane has much higher energy content per volume. And then if you go up to liquids, right, you can get gasoline has more energy. Diesel fuel has more energy. Methanol, ethanol, right? So hydrogen's not your choice for energy density. And if you wanted to pack a whole lot of energy into a small space, there are limited choices for hydrogen. You got to compress it into a cylinder at 2,500 pounds per square inch, right? So you've got a hazard rolling down the road if you want to put it in your car and run off of hydrogen. Besides that, it won't take you very far. A couple of 100 miles and you're out. So other types of hydrogen storage are being investigated, of course, but nothing competes with the internal combustion engine using fossil fuels. But the one advantage of hydrogen is that it only produces water as a byproduct of combustion. All right. So let's see, what's this? 79. 79. All right, what are we asked here? Which of the following is not being considered as an energy source for the future? Well, we've got numerous examples of ethanol used, methanol, seed oil, shale oil. All of those are good, either biological origin or fossil fuels. Carbon dioxide is not a fuel, right? Carbon dioxide is the product of combustion, right? If you take any fossil fuel, let's just take an easy one, like methane. Methane combines with oxygen to yield carbon dioxide and water, right? That's not balanced, of course, but it gives you the idea that this is a fuel, that's the waste product. All the energy contained over here has been spent by producing those products, and we get energy out of it. That's an exothermic process. Okay, now we're going to learn in the second semester why carbon dioxide is not an energy source, whereas methane is. But we'll save that for a later date. All right, let's see what else we can find. 90, okay. A gas absorbs 188 joules of heat and performs 310 joules of work. The change in internal energy of the gas is what? All right, let's draw a picture. All right, if we have a gas like this, and let's say it's let's say the piston is down here, right? And we got a gas down here. Okay. Now, this is our system, right? The trapped gas is our system. It absorbs 188 joules of heat. So the Q is going in. That means it's positive. In fact, it's positive 188 joules. But then, after we add the heat, the gas expands, right? It comes up to here, maybe. And when it does that, it does a certain amount of work on the surroundings. Right? So that means work is leaving the system. If the gas does work on the surroundings, work is leaving the system. So this W is a negative to the tune of 310 joules. Okay, so now our formula being Q plus W, then Q is a positive 188, but a minus 310. Okay, so we got, let's see, 2, let's see if I can do this in my head. 8 from 2 and 8 from 10 is 2, and then 122, negative 122 joules. Okay, so C is the answer. The change in internal energy is negative. Internal energy is leaving the system. That's why it's negative. All right. Let's see what we've got on the menu here. Number 99. Okay, nitric acid, HNO3, was first prepared 1,200 years ago. When will that be? 1,200 from 2,300. 1,100, right? 1,100 AD. All right. By heating naturally occurring sodium nitrate, or saltpeter, with sulfuric acid to produce sodium bisulfate and collecting the vapors of HNO3. All right. So, and the equation that determines, that is associated with that process, is right here. There's the saltpeter, NaNO3, and plus liquid H2SO4, yields sodium bisulfate. Whenever you see bi in the name, that's an archaic form. It's part of a trivial name. Bi means hydrogen. So if we started off with sulfate, polyatomic ion, and we add a hydrogen to it, that's hydrogen sulfate now, but it used to be bisulfate. And this would be only a -1 charge. That's why you only need 1 sodium with this one. Same as when we were doing our experiment today with sodium hydrogen carbonate, sodium bicarbonate, right? Or Arm & Hammer baking soda. All right, so it'd be sodium bicarbonate. Okay. All right, so that's sodium bisulfate plus HNO3. HNO3 gas. Now, I'm not sure how they collected that HNO3 gas. My guess is that as the gas was produced, they channeled it over and bubbled it through water. And if you do that, then it turns it into HNO3 aqueous, or nitric acid. Okay, so what we want to do is determine the delta H of this reaction. Remember the formula, right? It's in your useful information. The formula for doing this, if we know all these values, all these heats of formation for the various compounds, all we have to do is add up all the heats of formation for the products and subtract the heats of formation for the reactants. Okay? Very simple. But you have to watch your signs and the number of moles. That's what this means. If we had coefficients in here, then we would have to multiply the respective coefficient times the heats of formation for each one of these. Why? Because the heat of formation is based upon 1 mole of the compound. So if the equation has a coefficient, you need to multiply that times the heat of formation when it goes into this equation. But each one of these, and this is balanced, right? 1 sodium, 1 nitrate, 2 hydrogens, 1 here, 1 here, 1 sulfate, right there. Okay, so we're good. It's balanced with all the coefficients are 1. So we don't have to multiply the heats of formation times anything but 1. And of course, 1 mole will cancel out the mole, and we're left with only kilojoules. All right, so to put this together, we need the products first. Sodium bisulfate, which is minus 1125.5. And this is kilojoules, correct? All right. So let's add HNO3. Minus 135.1 times 1 mole is minus 135.1 kilojoules. That's the products. Now we subtract the heats of formation for the reactants. First one is saltpeter, minus 467.8. And then the next one is H2SO4, minus 814. Minus 814.0 kilojoules. And that's it. All we have to do now is crunch the numbers and watch the signs. Right? This one over here, 1125.5 and 135.1 is minus 1260.6 kilojoules. And this one is 467.8 and 814.0. This is a minus 1281.8 kilojoules. Okay. But there's a minus here. So that minus times this minus makes this a positive. So we have a positive 1281.8. Okay. So we take that one and subtract this one. And I get 21.2. And it's positive. This positive is bigger than that negative. So that's positive kilojoules. 21.2 kilojoules. C is the answer. All right. Takes care of that one. And unless I missed my guess, I think this is the last one. Yep. That's all the ones I had highlighted. Okay, since this was a review, the next time we meet will be the exam number 4 on chapter 6.